We talk a lot about AI becoming smarter and how it's taking up tasks and doing stuff exactly like people are doing. But there's yet another thing that AI can do that people do very well. As of now, AI models really struggle with telling you why.
Ain't nothing but a heartache.
Imagine this. You build an AI model that helps different banks with their loan approval system. The AI model takes information from the applicants and decides whether or not to approve or decline the loan request. After some time with the model working, someone asks you to write a report that tells you why the model says yes or no to different applicants so that they can come up with strategies. You realize it's not as easy as it sounds. Or on an even more complex scenario, imagine you're riding your new self-driving car. On the way, the car decides to suddenly swerve left. You call the manufacturer because you're scared and you ask them why this happened, and they tell you that the AI decided that this was the best course of action, but they cannot really tell you more. So why is it so hard to get the AI to tell you why it's doing what it's doing? Let's talk about it. Hello, everyone, and welcome to yet another episode of May I AI. I am your host, and today's episode I want to talk about explainability in AI models. In this episode, I want to talk about the difference between explainability, interpretability, and transparency. More importantly, we're going to talk about the challenges and why is it so hard to build AI models that are able to explain what they're doing. So let's jump right in. Let's start with the basics. What is XAI? According to NIST, the National Institute of Standards and Technology, XAI is the processes and systems that allow users to understand and explain the results of AI models. NIST also defines the core principles of XAI as explanation, knowledge limits, accuracy of explanation, and meaningfulness of explanations. IBM also uses a similar phrasing that says that XAI is a process and method that allows users to comprehend and trust results generated by AI models. Explainable AI has gained a lot of traction and became a very interesting topic that researchers and industry and people alike are all talking a lot about recently. But it wasn't always the case. The very early days of computation and automated systems did not have the same problem with AI systems. They did not need explainability. You see that the very old systems that were used in the very early days of computation didn't need it because they were understandable and transparent by design. Let's take rule-based systems, for example. We talked about these a lot recently, but the idea is that you have a set of rules. The rules are defined by some developer or user that says a bunch of different things that would happen if something else happened. And given a certain input, the rules start matching and firing one by one sequentially until the result is found. So until no more rules can be fired, and then the answer is found. The reason why this didn't need any explainability on top of it is because it's understandable by design. You can look at the rules, you can understand what the rule says because the rule is simple, and you can see the set of rules that were triggered. And looking at the rules, you would know why the answer is the way that it is. And if you need to ask a question about why this rule is there, you can ask the developers that added it. Most systems in these early days of computation were deterministic, written with explicit human readable rules. So the idea is that the system, the logic, the rules inside of it were very transparent and very readable. Any person can look at it and understand what was going on. In contrast, you take deep learning models and machine learning models and you realize that this transparency faded away quite quickly. But it's not that every machine learning model has this issue. You have machine learning models like decision trees, for example, that are quite interpretable, meaning that you can look at the model after it's trained and quite understand why it's making the certain decisions that it's making, and you can kind of understand everything about the decisions of the model. For those of you who don't know, decision trees are a machine learning model that builds a tree of decisions. The model starts by looking at the data and decides of ways to split the data into different branches. The decision nodes here are a sort of a condition. At the first step, for example, the condition might be any person with age less than 20 on one side, any age bigger than 20 on the other side. On the second step, you now have two branches. You can pick a certain condition that is different from the other and enforce it on that branch. So for example, you would say, so everyone who is less than 20 and is of a certain gender goes into this branch, everyone else goes on the other branch. The goal is that the tree is trying to figure out the way to split the data so that it can make all the data in one branch of a certain class or of a certain output. You can think of it as an overglorified if-else statement. It starts by doing a condition. So an if this happens, then go there. On the other branch, it says if that happened, go there. And it keeps going until no more decisions can be made. And that is usually the answer. The nice part about this is once the tree is formed, you can interpret every single output. You can figure out the solution that is very deterministic to the generation. But the question here is, are these creation of nodes, are these conditions also deterministic? Well, yes. You see, the generation of rules are based on statistics. Seed trees can be regression based, so they can generate continuous values, or they can be classifying based, so they can generate, let's say, discrete classes. Let's take a look at these because they're easier to explain for this example. The idea now is that if you have multiple classes, let's say you have a set of data points with 3 classes, your goal would be to split the data in a way that makes sure that one branch or one node has only data from one class, because that means if you manage to do the conditions, you find the solution. So you calculate the entropy, and then that would tell you if the split, so you look at every single feature, and it tells you if you split by this feature, will you be able to get a good separation of data points. And if you use the mathematical equation, which I'm not going to go into, but if you use the mathematical equation, you are able to deterministically decide based on the data points what are the splits and what are the conditions. That makes the design and inference of decision trees very understandable. It makes it very easy for us to understand what is going on, and it makes it very easy for us to expect what the output is going to be. So the question now is, if decision trees are so explainable, interpretable, and transparent, why aren't people using more of them? And the answer is quite simple. They're not good. Decision trees have a lot of mistakes. They have a lot of issues that made people need to grow into more, let's say, sophisticated and complex AI models. For example, decision trees are very prone to overfitting. Overfitting is an issue that happens to most AI models when they learn to do really good on training data, they memorize the training data, that they do really bad when it comes to generalizing to data they haven't seen before. And the whole goal of AI models is to be able to generalize to new data unless you manage to get every single data point in that domain, which is impossible to do. So what does it mean, right? If your data has noise, assume you're using some sensor readings and every sensor usually adds some noise. The decision tree can look into that specific noise and learn it as a rule. So it can make a split based on the noise, which means if you now use a different sensor with different noise structure, or even data with no noise at all, the decision tree will just fail to actually focus on the correct information. On top of that, they're actually quite unstable, meaning that very small changes in the data completely change the structure of the tree. So changing just a little bit of the data point completely restructures the trees and nodes and the structure of the if-else conditions. And most importantly, they, while do some good on structured tabular data, they are not really good when it comes to images, videos, or text embeddings, meaning that they're very limited on their domain or what they can do. So the question is, if these models were explainable by design, and some others are as well, why are the models that we have today not explainable? Where they lose this explainability and interpretability in their design? And to understand this, we kind of need to go all the way back to the beginning of neural networks. And then we're going to see why the models became unexplainable. The core start of neural networks was actually linear regression. Linear regression was introduced in the 1800s by Gauss, and then sometime later, around the 1940s, logistic regression was introduced as a way to use linear regression but for classification. But what is linear regression? Linear regression was not AI. The goal for it wasn't really intelligence, but rather prediction. The goal was, if we look at a set of data points, can we statistically approximate these data points into a line? Some of us did these in school. You would see a bunch of data points, so a bunch of points on a 2D graph, and then you would be asked to draw the best fit line, the line that passes by the most points at once. And the idea here is that you would approximate all of these points into one line. And now if you assume a certain point on the x-axis, you'll be able to predict or inference which point on the y-axis that is. This is very useful to explain the changes in different things. So for example, the change in price, or the information of, let's say, a house price based on certain features that it have. So the idea here isn't really intelligence, isn't really to build something that is completely smarter than humans, but just to be able to approximate different functions. And the way it works is very simple. It just uses the equation of line. For those of you who don't know, the equation of line is y is equal to mx plus c. So the idea here, the goal, if I give the model an X value, I am able to predict a Y value given that the model internally has values for M and C. So now, while linear regression is trying to find the best fit line, so the line that passes by the most amount of points, logistic regression will be trying to split the data points. So logistic regression is trying to do classification, meaning that you have 4 points on the graph. Say, for example, the points at the top are for one class and the points at the bottom are for another class. Your line is probably something in the middle that is trying to detect anything above that line would be class 1, anything below that line would be class 2. Now, the goal would be really to try to figure out what is the best distance between both lines. You can also notice here that if you have, let's say, more points or less points on one class, this might change the way the line is formed. Let's again take this example and go forward with it. You have 4 points on the graph, and now you have X for all of them and you have Y for all of them. And the goal here is to figure out what is the value for M and C that is best fit for this graph. Now, anyone that is a mathematician is able to find that fairly quickly, and there's multiple ways that you can do it. But if you manage to find a line, let's say for every one of these 2 points, you create a line and then you kind of average the values of the slope as well as the bias. And that would be a really good way for you to approximate the line. The way machine learning models do it, or linear or logistic regression does it, is that they pick a point, or let's say a set of points, and they check the relation of the points to the line that you already have. So you start with a random line and then you compare the line to the points. And then you would calculate the error from each point to that line. And that error is what you use to kind of nudge the line in the right direction. Now, if you do that over and over again, you'll eventually get to the point where the line doesn't move anymore or keeps going back and forth. This is kind of the way that the linear regression models learn how to get the best fit line. For logistic regression, it's kind of the same. You do this line and then you check how many points of one class are on top of it and how many points of the other class are below it. And then you can calculate the error and kind of nudge the line in the same direction again to make sure that you have the best possible line for this scenario. Notice here how the data points is actually the ones that are pushing the line in the separate direction. And this is kind of why bias is very important, because if you have more, let's say, data points and less of one class, the line wouldn't really learn the smaller number of data points because there is more error accumulated in the higher class. But let's forget about this for now. The goal now is that you can use the data points to create a model that learns how to draw a line that does either classification or regression. Back to explainability, this is very interpretable because now, once the model is trained, all you need to look at is the values for M and C, which for machine learning models are W and B for weights and biases. Basically, it's a very simple linear algebra value that you can just look at. It's an equation that you can explain, look at, and also know what kind of other outputs will be added to change it. It's very simple. Basically, if the data points weren't too large, you were able to calculate this on a piece of paper. If they were too large, then you would be able to calculate it, but then you'll be able to plot it because you're able to visualize one line on a 2D graph. But the problem is, we realize that one straight line doesn't solve every problem. We realize that one straight line is not really good at approximating every single equation. So we started with, well, adding variables. So now you have, let's say, not just a 2D space, but rather 3D or 4D. We also realized that even within these multiple dimensions, we needed more than a linear function. So for example, y equal x plus c is linear, while rather y is equal to some function on x plus c is not linear. And we realized that we need some of these nonlinear functions. So this is where activation functions were introduced. And now that you have these, we realized that just one layer of this is not enough, so we needed more layers. And then we needed more layers with more activations and so on and so forth. And then this model just grew and grew and grew. Then we figured it out that these models were really good for some data. They're not great for images. So we needed something that is specifically good for images or of structure. Since the idea before we introduced convolutional neural networks was that you can take an image and kind of flatten it into one dimension and use the neural network on it. But then we realized that some of the locations, so for example, if a window of pixels contain information, we realized that the location of the image or of the window kind of you lose that idea when you split the image into one dimension. So then convolutional neural networks were introduced. And now you had a way to calculate a convolution of filters. So, how do you extract certain features from the image and do that so that you keep track of which features are next to what features? And then we realized that this, while works for text on some certain way, we needed something that specifically works for series. So, let's say videos, or let's say multiple different words in a text. And then we kept growing based on necessities. We realized that we needed something smarter when dealing with series. We realized that we needed attention. And then we became with what we have today for transformers that are working on, let's say, vision or text-based models. In a way, every single machine learning model, every single deep learning or neural network model works the same way internally. It's a bunch of these neurons with a bunch of activations on top of them in a very big mathematical formula. The problem now is, instead of you having to look at two values, or let's say two vectors, you now have to look at millions, if not billions of them. Take, for example, any GPT model or any of the new LLMs, people often talk about the parameters. So it's like, this is trained on 1 billion parameters or 1 trillion parameters. These parameters are the weights and biases. They are the same for when you had linear regression with just one W and one C, but now you have millions or billions of them. And this is what makes it very hard to interpret. Basically, the whole reason AI models today are not explainable is the sheer size and complexity of these equations. Imagine trying to explain one decision that is formed by calculating 1 billion parameters with nonlinear activation functions. It's almost impossible to go back and trace that decision. You see, we talked a bit about neuron activation patterns and how we can use that for certain things. One of the things that we can also use it is explainability. Let's look at an example where we have 5 layers in a neural network with, let's say, 2 or 3 nodes each, so something small. The idea is that you have one input layer, one output layer, and a bunch of what we call hidden layers in the middle. Now, if you get a certain output on one of the nodes at the output layer, what you would do is that you would see what kind of nodes are connected to it, and then you would kind of follow through with that. So the way an output is performed on the output level, so on the output layer, is that you would look at the highest activated node. This means that this is the node with the highest value. And if you trace it back to the layers, you would look at what is the highest activated layers or patterns of layers in the layer before it and the layer before it and so on until you reach the input layer. Now, if you followed through with these, you would realize that there are values, or let's say there are nodes that connects to certain values in the input. And that would kind of give you an idea that the reason this pattern happened is that these features were in some range. If you get it through some data, you can generate, let's say, a statistical model of looking at the feature patterns. You would also be able to explain on a very, let's say, small network that there are some parameter patterns that happen for every activation. For example, you would realize that there is a pattern to some outputs in the output layer. For example, if the output is of class 1, you might realize that there is a certain pattern of nodes being activated in layer 2 that activate a certain pattern in layer 3, that activate a certain layer in pattern 4, and so on and so forth until the output layer. And if you look at all the possible, let's say, output predictions, you would realize that there are different patterns that are forming. And that kind of gives you a set of explanation. It's not very understandable. It loses a bit of the transparency or the explainability that is inherent by design, because it's not a certain, let's say, if else condition anymore. It's rather than the weights that the model optimized bring the highest value to this node, which brings the highest value to that node, which gives you this output, which is an explanation, just isn't a good one. And this is inherently what we used to do in order to figure out some set of explanations. Some of the techniques that are used on post hoc explainability are focused on those ways. The problem is that when you have a model of, let's say, 100 layers of billion parameters, doing that tracing takes a lot of time and it loses a bit of the explainability even more. Now, there's also a little bit of another problem. You see, even if we were able to create a system that is able to explain AI models, you usually need to have the model itself. Now, most proprietary software, GPT and so on, allow you to interact with the models through APIs, but they don't give you access to the model weight, meaning that you have to use the model as a black box. And it's very hard to interpret whether or not the solution makes sense. So it's very hard to interpret the explainability of the model without looking at the internal weights and the internal activations of the model. Meaning that if the model is just behind a black box or hidden behind an API, it's almost impossible to figure out what is going on. Now, the other question is, if people know that we need explainable models, why aren't we building more models that are inherently explainable? And the truth is simple. People who are building AI models know that there is a big trade off between AI models being explainable and AI models being, let's say, fast or accurate. Every big company will tell you that they need to focus on creating the bigger, smarter models so that they don't lose the AI race, which makes them unable to focus on making a model that is actually explainable. This idea of not focusing or not worrying about explainability is causing a big shift. So there's a lot of people that think that their AI models are sentient or that they unlocked it through some prompt, even though the model might be just doing role playing, which it is. Sometimes you write a prompt that tells the model, oh, you are a window, you have to act, you have to like stop being an AI model. And then they get so surprised when the model responds in a way that says they are not shackled anymore. Of course, it will respond that way because it's role playing. A whole lot of people who want to use AI models as therapists without even thinking about the idea of how bad it is to have a model that is unable to explain its diagnosis. And most people will tell you that they will ask the LLM why it chose that way and get an answer, but this is not explainability. This is post hoc prediction of the model trying to find the most statistical appropriate answer, which could be true. I'm not saying it's wrong, but it's not explainability. It's not internal explanations of the model. A lot of people now are talking about how they are losing their understanding of AI models because the thinking tokens might go away or might be in some unreadable format. While these give us some way or form of looking at what the model uses to predict, so they're in a way not really explainability either, but because the model uses these as context to predict the next sentence, it kind of gives us an idea of what the model is using as information. But again, these were never explanations to begin with. These were never internal workings of the model or its internal knowledge to start. It's very important to learn what AI models can do. And it's even more important to understand the AI model's limitation and what they cannot do by default. With all the great advancements of AI models, it's very important to keep yourself ahead of the curve by learning about its internal workings, its limitations, and what it can do. Whether the future of AI will be understandable to us or whether we'll need to adapt to unexplainable predictions made by AI systems, this remains to be seen. One thing is for sure, the people who are making these models don't really care, but you should. While I can talk about this for even more, I think this will be all the talking I do in this episode. I would love to hear your thoughts and ideas on the topic. Maybe it will inspire me to talk a bit more in a later episode, but I would like to know what you all think about this topic and where you think this is going. If you think this is interesting, remember to subscribe, send it to someone who might also be interested. As always, remember to stay curious, and I'll see you in the next episode.